Section 11.3, Properties of Logarithms. So in this section we're going to look at a couple properties of logarithms and see how that can help us solve equations. So the first one is the exponential/logarithmic forms property, and it says if a is greater than 0 and b is greater than 0 and b does not equal 1, then the equations the log base b of a equals c and the equation b to the c equals a are equivalent. This is one that we were using in the previous section to help evaluate logs. We were taking a log we were trying to evaluate, setting it equal to some constant, and then saying the base raised to that value was equal to the inside. And that's just saying that those are equivalent forms. The base to the other side, b to the c, equals the inside of the log, which would be a. So let's just practice that by rewriting a couple of these logs into exponential form. So the idea of the equivalence is that if you want to rewrite a log as an exponential form, you take the base, you raise that to the other side, or what the log is equal to, and that should be equal to what was inside of the log, which would be the 32. And if this was a valid log statement, this would be also, and 2 to the 5 is 32, so that does check out. And then they want us to do that on this one with letters. Because it's all variables, we can't check it, but we can still rewrite it. It's the base to the other side, so the base to the other side would be r to the t, is equal to what's inside of the log, which would be equal to s. So that's the idea of rewriting a log into an exponential form. Now the reason that we might want to do that is it can help us solve equations. So let's look at a few examples of that. If you have the log base 2 of x equals 3 and you're asked to solve, one way to do that would be to rewrite it as an exponential. So take the base, raise it to the other side, and that should be equal to the inside. And now all of a sudden we have an equation that's pretty easy to solve for x, and in fact it's already solved for x in the sense that x is by itself. We just need to work out what x is equal to. It's 2 to the third, and 2 to the third is equal to 8. So by rewriting that log as an exponential statement, we were able to find the value of x. Here's another one. What we have to remember on this one is that if no base is written on a log, then that's a common log, and so it's log base 10. So let me rewrite it that way first. Log base 10 of x equals -3. And now I want to rewrite it without the logarithm, so I want to use the property up above, which says the base to the other side. So that would be 10 to the -3rd is equal to the inside, which would be x. And again, the x is already by itself, so all we need to do is figure out what that x is equal to, or simplify what it's equal to. We already know it's equal to 10 to the -3, but we don't like the negative exponent, so I would make a reciprocal to get rid of the negative sign on that exponent, and then I would work out 10 to the third. 10 to the third would have 3 zeros on it, so that would be 1 over 1,000. Moving on to part C, let's look at another one. We have 3 times the log base 5 of 4x plus 1 equals 9. Now all of a sudden this is substantially messier than either of the two that came before. And I want to use that same property, but before I do that, if I look up here, it has to be just the log of something. There can't be a number out front. So this 3 that's out front is actually kind of getting in the way of me using that log property. So what I'm going to do is get rid of that 3 before I rewrite this as an exponential function or form. So the 3 is connected to log base 5 by multiplication, so I'm going to divide to get rid of it and cancel those 3's. When I divide one side by 3, I have to do the same thing on the other. So after I do that division, now I have the log base 5 of 4x plus 1 equals 9 over 3, which would simplify to 3. Now I have just a log, a base, an inside, and the other side, and I can apply the property that says that's equivalent to the base to the other side, 5 to the third, and that would be equal to the inside, 4x plus 1. So again, the base of the log raised to the other side of the equation equals what's inside of the log. That becomes 5 to the third equals 4x plus 1. From there, I just want to simplify. 5 to the third, if I work that out, is 125. So that's equal to 4x plus 1. And now I'm just trying to solve for that x. So subtract 1 from both sides to cancel those. So 124 equals 4x. Trying to get that x by itself, divide both sides by 4. The 4's cancel. And I get x equals, let's see, 4 goes into 124, 31 times. So that would be the solution to that one. So the key step to remember on this is that if you're trying to rewrite a log as an exponential, it has to just be a log. So if there's any other number out front like that, you're going to have to divide to get rid of that before you rewrite in exponential form. Alright, let's look at another example. This one is a little bit messier, so we're going to end up bringing in our calculator and doing an approximation before it's done. But we're trying to solve for b in the log base b of 95 equals 9. So let me rewrite that down here by itself. Log base b of 95 equals 9. I want to use the same trick I've been using on the last ones, which would be to rewrite this in exponential form. So take the base raised to the other side, the base is b, raised to the other side, which is 9, and set that equal to the inside, which would be the 95. So I've rewritten it as an exponential form, and I want to try and solve for b now. So to get b by itself, I have to get rid of that 9, and what would cancel a ninth power is a ninth root, or raising both sides to the 1/9 power. So I think it's easiest to see it as this 1/9 power. Think about our rules. A power to a power you multiply, and 9 times 1/9 would be 9 over 9 or 1, and b to the 1 is just a b. So in essence, when you have a ninth power and you raise both sides to the 1 over 9, those cancel out. And so what would b be equal to? The 9 and the 1 over 9 have canceled, so b is equal to 95 raised to the 1/9. And I wrote this in a little bit of an odd way, but that's because that's what it would look like in the calculator. And the calculator should be brought in here because they said to approximate our answer to 4 decimal places. And this would be a ninth root. I don't know what the ninth root of 95 is in my head, but I can do it on the calculator and approximate it to 4 decimals. So I'm going to do that. So I take 95 and I raise that to the 1/9 power. Remember, when you're raising things to fractional powers, that the fraction has to be in parentheses, otherwise that won't work quite right. And then there's my answer, and I want to approximate it to 4 decimal places. So b is approximately 1.658, and the next digit is a 6, and followed by a 2, so we'd keep it as a 6. So there's our answer. So this is a lot like the problems we did on the previous page, where we have a log and we rewrite it in exponential form to try and solve. But what was different is this time our variable was the base, and when that happens and you have the base to some power, you're going to want to get rid of that power by doing 1 over that to both sides. And so in this case that means taking a ninth root, but in any case we're going to do it on the calculator and just get an approximation. Alright, let's go ahead and look at the other property that's used in this section to solve equations. This is called the power property for logarithms, and it says if x is bigger than 0 and b is bigger than 0 and b is not equal to 1, then the log base b of x raised to the p is the same thing as p times the log base b of x. Okay, that kind of, even to me, sounded like a lot of gibberish. Let's see what their translation is. In words, a logarithm of a power of x is the exponent times the logarithm of x. Alright, maybe still a little bit hard to understand. So let me show you what that property is saying. It's saying that if we take the log base b, or have the log base b of x raised to some power, that power can be taken from inside the log as an exponent and brought out to the front as just a factor. So if you look at what's happening on the left compared to the right, that exponent of p, when we move to the right, is gone, but it's moved out to the front. And that's what this property says. If you have an exponent inside of a log, you can bring that out to the front as a factor. And we'll see in a moment why that's useful in solving equations. Another property is called the logarithm property of equality, and it says for positive real numbers a, b, and c, where b is not 1, the equations a equals c and the log base b of a and the log base b of c are equivalent. And if you think about what that's really saying, it's saying if you have a equals c, you can take the log base b of both sides. So this just brings in another tool that we can use when we're solving equations. You can take the log of both sides of the equation, and you can do that with the log of any base as long as the base is not 1. So let me show you some examples of using those two properties to solve equations. Starting off with 10 to the x is equal to 50. We want to solve that for x, and we'll round any answers to 4 decimal places. So I know that 10 to the first is 10, and I know that 10 squared is 100. So in order to raise 10 to some power and get 50, it probably has to be 1 point something, but I don't know exactly what it is. So what I'm going to try and do to solve for the x is use this property where you can take a log of both sides. This is a step you'd want to do anytime your exponent is a variable. And you can take a log of any base, but since the base here is 10, it would be best if we used a base that matched. So I'm going to take a log base 10 of both sides. So remember that if you just write log, that's the common log or log base 10. So I'm going to just take the common log or log base 10 of both sides. And then logs and exponential functions are inverses. So we don't have to write the base here, but it is a 10. And when the base of the log and the base of the exponential inside match, they cancel out. So the log base 10 and the 10 just cancel, and the x would be all that's left over. So that gives us x only, because the log base 10 and the 10 cancel, just leaving the exponent, is equal to the log of 50. So this should be my answer, but they want it approximated to 4 decimal places, so I'm going to bring in the calculator. It's really important that I took the log base 10 because that's a log that is on the calculator. So I can go to the calculator at this point, enter in the log base 50, and that would be an approximation for my answer. So let's see, the common log key is right here. So I'll go ahead and press the log key, and I want the log of 50. And remember, just going back to the kind of logic of it, if I do 10 to the first, it's 10, so that 1 is too small of an answer. If I do 10 squared, it's 100, so 2 is too big of an answer, so this should be 1 point something. So let's see if it comes out that way. So I get 1.6 something, and let's round that to 4 decimal places, 1.69, and then it's an 89 but followed by a 7. So if I think of that as an 89 and then I see the 7, I have to round it up, that would become 89 rounds up to 90. So I'd put 1.6990. Now that might have been a little bit of a weird step, and maybe this felt weird where I canceled the log and the 10, so let's check the answer. If x is really the answer, then 10 raised to the 1.6990 should be 50. So let's take 10 and raise it to the 1.6990, and we should get 50. Instead we get something close to 50. That's because I rounded this. If I go back and look at the log 50 again with all its decimals, if I take 10 and raise it to the answer, then that's going to substitute all of this in there, not just the first 4 decimals. And if that's really the right answer, then 10 raised to that x should be 50, and that is what happens. So it looks like that works. Alright, let me go ahead and show you another example that is going to use both of the properties this time. So I'm trying to solve for x, and x is an exponent. So the first step is to try and get that base by itself, which means I need to get rid of that 3. So that 3 is connected by multiplication, so I'll divide both sides by 3, and those 3's will cancel. On the other side, they don't cancel. I just get 17/3. And I'm just going to write that as 17/3. I'm not going to go to the calculator, because if I did, I'd get a decimal, which I would end up having to round. Now I left some space here, and you'll see why. We said on this one that when your variable is an exponent, you should take a log of both sides. So my variable is an exponent. So after I get the base by itself, the next step would be to take the log of both sides of the equation. And I'll put parentheses around this because it's the log of that whole fraction. And this time, the base of the log is 10 because it's a common log, but the base of the exponential is 2, so they don't cancel out. But I can still use this property that says if I have an exponent inside of a log, I can move that out to the front, and that would be equivalent. So I'm going to take that x right there, and I'm going to move it out to the front of this equation, or of this expression. So that becomes x log 2. So the log 2 part stayed put, but the x moved out front is equal to the log of 17/3. And now this x is connected to log base 2, or log of 2 by multiplication, so I can get rid of it by dividing both sides by log of 2. And those log of 2's would cancel, and here's what x is equal to. And they asked me to do it to 4 decimal places, so I'm going to put that into the calculator. So let's see what that looks like. So clear out that old stuff, and entering that in, first the numerator, common log of 17 thirds. Make sure that that whole expression 17 thirds is inside the parentheses, and then divided by the common log of 2. And they always open a parenthesis on the log on the TID4, so I'll just close that up. So that's log of 17 thirds over log of 2. And I get an answer of approximately 2.5. They want me to round that to 4 decimal places, so 2.5025 would be 1, 2, 3, 4 decimal places. Now, if that is really the answer, if this process really worked, then if I take the left side and I plug that value in for x, I should get the right side. So I'm going to do 3 times 2 raised to that answer I just got. So that's 3 times 2 raised to my answer. That should be equal to 17 if that answer is correct. So let's see. Yep, 17. So that looks like it checks. Alright, let's go ahead and have a look at one more example. 20 equals negative 3 plus 4 times 2 raised to the x. What we need to notice right away on this is that the variable is our exponent. And when that happens at some point, you're going to want to take a log to bring that exponent down. But to make that work, you have to get the base by itself. So you have to get rid of the negative 3 and the plus 4. So the first thing I would do is get rid of that negative 3 by adding 3 to both sides. And if I do that, the negative 3 and the plus 3 cancel, and on the left I get 23, and on the right I get 4 times 2 raised to the x. I still need to get that base by itself, so I have to get rid of that 4. It's connected by multiplication, so I would divide both sides by that 4, and that would cancel those. And then on the left I have 23 over 4, and on the right I have 2 to the x. And I've purposely left space in front because once you get that base by itself, the way you bring that variable down is to take a log. And if I'm going to take a log on the right, I'm going to take a log on the left as well, and remember when it's a fraction it has to be a log of the whole fraction. But the reason we do that is because of that property of logs that says when you have an exponent in a log, you can move that to the front. So if I rewrite that, and I'll go ahead and switch sides here, that x comes down, I still have the log of 2, and on the other side I have the log of 23/4. And then I want to get that x by itself, so that means I'm trying to get rid of the log 2, which is connected by multiplication. So if I divide both sides by the log of 2, that's going to cause these to cancel out. And if I do that division on the left, I have to do it on the right also. And then that tells me what x is. X is equal to the log of 23/4 divided by the log of 2. But remember from the previous page they were asking us to approximate these answers to 4 decimal places. So I'm just going to put that into my calculator and see what I get. So we have the common log, log, of 23/4 divided by the common log of 2, and making sure that the 23/4 is in parentheses and the 2 is in parentheses. And I get approximately 2.523, and it's a 5 but followed by a 6, so I'll round that up and make it a 6. So my answer is approximately 2.5236. And then just to check that answer, I'm going to plug that into the right side of the equation where the x is. Negative 3 plus 4 times 2 raised to the x. But my x is this answer, so I'm going to hit the answer key by doing second answer. And when I plug that in, if this is really the answer, this 2.52356, then I should get the 20 that's on the left side. And I do, so that's a good check on my work. Alright, let's go ahead and look at one last example. Let's use the intersect feature of the calculator to solve log of x plus 1 equals 3 minus 2/5 times x and round any approximate answers to 4 decimal places. So it turns out that this equation with a log on one side and kind of a linear equation looking piece on the other side is one that I don't know how to solve by hand just using algebra steps. And whenever we get something like that, we can always take the left side and make that y1 and take the right side and make that y2, and using the intersect feature would tell us where the two pieces are equal to each other. So let me bring the calculator in. I'm going to go to the y equals menu. I have an equation there, so I'll clear that out. And I'm going to enter the left side, log of x plus 1 in parentheses. And then for y2, I'll enter the right side, 3 minus 2/5 times x. And then for the window, I'll just go ahead and choose zoom standard, which is the -10 to 10 window, and we'll just take a look at how that looks. If we don't like it, we can always adjust. So I'll hit zoom standard and see hopefully my two graphs. And there they are. So that is kind of small. There's no intersection going on over here. It looks like everything's on the right side. So I'm going to adjust the window just to go from 0 to 10 and maybe like from -5 to 5 to get a closer look. So 0 to 10, -5 to 5, and let me graph it again. So this is kind of zoomed in on that a little bit. So you could have left it alone, but I like being able to see it a little bit better. So I can see the intersection. And let's see, what's my scale here? I think that it's 1s. Yeah, the scale on the x's is 1s. So that intersection, let's count the tick marks. 1, 2, 3, 4, 5, 6. It looks like it occurs just a little bit before 6. So maybe that's around 5.5, something like that. So to find that out, we want to go into the calc menu, choose intersect. Is the log my first graph? Yes, press enter. Is the line my second graph? Yes, press enter. For the guess, I'll just move over a little closer, but notice it still says question mark. So if I want to confirm that that's my guess, I'll press enter again. And then it'll switch from saying guess to telling me what the intersection is. And I guessed it was about 5.5, and now the calculator is telling me it's 5.47234457. We were asked to approximate it to 4 decimal places. So I can say that x is approximately 5.47, and then let's see, we have a 2, 3, and it's followed by a 4, so we would round down and that would stay at 2, 3. So here's one we don't know how to solve with algebra, but if we enter y1 for the left side, y2 for the right side, then we can choose calc and intersect, and that helps us to find the equation. Alright, that wraps up section 11.3.